probability, permutation, and combination. These topics are indeed very important. The concepts are worthwhile to consider, for they always apply in our daily undertaking. The importance of probability lies in its role in inferential statistics. While statistics focuses on its use of information concerning a sample to make inferences about the nature of the population from where it is drawn, probability provides a measure of certainty attached to the statement regarding the population. Probability is a possibility or a chance to be true or to happen. Randomness of sampling as the best introduction to probability concepts is meant to promote more rational statistical decision-making under conditions and uncertainty. Any activity or process that has a number of outcomes is called an experiment. An experiment is often conducted in several trials to generate a set of data. It is a sort of prediction after several trials with a chance result. The result is stated in fraction, decimal, or in percent. The set of collection of all possible outcomes of an experiment is called sample space. The sample space of an experiment consists of elements or sample points such that to reach outcome of the experiment, there corresponds exactly one element in the sample space. Sample space is denoted by sigma, or S. Tree diagrams, tables and graphs are often used to represent the outcomes of experiments to facilitate counting of elements of sample spaces. What is a sample space? Suppose you want to determine all the possible outcomes in tossing a fair coin twice. Tossing a fair coin is your experiment. While all the possible outcomes are your elements or sample points, sometimes called also as observations. These elements or sample points are contained in your sample space. Illustration: in a single toss of a fair coin, what are the possible outcomes? Let S be the sample space. Using a bracket, the possible outcomes can be contained. That is, S equals head, tail. The head, H, and tail, T, are the elements or sample points of the sample space S. Experimental probability. Experimental probability is a statistical expression of the prediction made from experiments with definable results. It is a process which is repetitive in nature but provides well-defined results. The formula is as follows: P sub S equals the ration of n sub st to Tn sub Tm times 100, where P sub S is the probability of success, n sub st is the number of success trials, and Tn sub Tm is the total number of trials made. Experimental probability. It is based on the data which is obtained after an experiment is carried out. It is the result of the number of occurrences of an event divided by the total number of trials. Example: a coin is tossed 20 times. It is recorded that heads occurred 12 times and tails occurred 8 times. Hence, probability of heads up is 12 over 20, or 3 over 5, since 12 and 20 are divisible by 4. Then, the probability of tails is 8 over 20, or 2 over 5, since the 8 and 20 are divisible by 4. Theoretical probability. This is based on what is expected to happen in an experiment, without actually conducting it. It is the result of the number of favorable outcomes divided by the total number of possible outcomes. Example: a coin is tossed. P of head is 1/2, and the probability of tail is 1/2. Consider this. Pizza toppings. Number of order. Mushrooms. 4. Pepperoni. 5. Cheese. 7. Black olives. 4. Now let us have the examples of experimental probability. Here are a few examples from real-life scenarios. A. The number of cookies made by Patrick per day in this week is given as 4, 7, 6, 9, 5, 9, 5. Based on this data, what is the reasonable estimate of the probability that Patrick makes less than 6 cookies the next day? Probability that Patrick makes less than 6 cookies is equal to 3/7 is equal to 0.428 or 43%. Why is it 3/7? That is because there were 3 days in which the cookies made by Patrick was less than 6, these are 4, 5, 5, and there were a total of 7 observations. Another example of experimental probability using the same observations. Find the reasonable estimate of the probability that while ordering a pizza, the next order will not be of a pepperoni topping. Based on this data, the reasonable estimate of the probability that the next type of toppings that would get ordered is not a pepperoni will be 15/20 equals 3/4 equals 75%. Why is it 15/20? It is because there were out of 20 orders, 5 were pepperoni, and the rest were mushrooms, cheese, black olives with a total of 15 orders. Probabilities. Probabilities can be added when a set of mutual event can be specified, when the probabilities associated with these events can be stated, and when the probability associated with a subset of these events is required. Another example. If you take out a single card from a regular pack of cards, what is the probability that the card is either an ace or a spade? Let X be the event of picking an ace and Y be the event of picking a spade. Then, the probability of X is 4/52, since there are 4 aces in a regular pack of cards. Also, the probability of a spade is 13 since there are 13 cards of spade. The two events are not mutually exclusive, as there is one favorable outcome in which the card can be both an ace and spade. Hence, the probability of the card that is both an ace and a spade is 1/52. Taking the sum of the two mutually exclusive events, that is, the probability of 4/52 for the ace, plus the probability of 13/52 for the spade. Their sum is subtracted by 1/52, the card that is both an ace and a spade. Since the denominators are the same, 52, copy it and take the sum of 4 and 13, that is equal to 17/52. Then subtract from the sum the probability of a card that is both an ace and a spade. So, 17 minus 1, since denominators are the same, we got 16/52, and since 16 and 52 are both divisible by 4, we got 4/13. The next example is: what is the probability of getting 3 heads and 3 tails if a coin is tossed 3 times? Solution: we know that, when a coin is tossed 1 time, then, the sample space is head, tail. This means that we can get either a head or a tail when a coin is tossed once. Now, since the coin has been tossed 3 times, hence, the total number of possible outcomes would be the following: first possibility, a head in the first toss, head in the second toss, head in the third toss. Second possibility is, head in the first toss, head in the second toss, tail in the third toss. Third possibility is, head in the first toss, tail in the second toss, tail in the third toss. Then, fourth possibility is, tail in the first toss, head in the second toss, head in the third toss. Then fifth possibility is, tail in the first toss, tail in the second toss, head in the third toss. The sixth possibility is, tail in the first toss, head in the second toss, tail in the third toss. Seventh possibility is, head in the first toss, tail in the second toss, head in the third toss. And finally the eighth possibility is, tail in the first toss, tail in the second toss, and tail in the third toss. Hence, THRE are a total of 8 possibilities or elements in the sample space. Hence, the probability of getting the 3 heads is equal to 1/8. And the probability of getting the 3 tails is also equal to 1/8. Getting the probabilities of 3 heads and 3 tails when a coin is tossed 3 times can be done by getting the sum of the individual probabilities. Hence, we have the probabilities of 3 heads and 3 tails is equal to 1/8 plus 1/8 equals 2/8. We simply copy the common denominator and add the numerators. But 2 and 8 are divisible by 2, we get 1/4. Ways of arranging items or objects in a definite order. If there are n times to be arranged all at the same time and none of these items should be repeated, the number of permutations is computed by taking the n factorial. The formula is as follows: the permutation p of n objects taken r at a time is equal to n factorial divided by n minus r factorial, where n is the total number of objects and r is the number of objects selected. The generalized expression of the formula is, how many ways can you arrange r from a set of n if the order matters? A permutation can be calculated by hand as well, where all the possible permutations are written out. Example of permutation. How many 3-letter words with or without meaning can be formed out of the letters of the word swing when repetition of letters is not allowed? Solution: here, n is equal to 5 since the word swing has 5 letters. Since we have to frame 3-letter words with or without meaning and without repetition, therefore total permutations are possible, that is, the permutation of the 5-letter word swing, taken 3 at a time is equal to 5 factorial divided by the factorial of 5 minus 3. Since 5 minus 3 is 2, we can cancel out 2. So, only the numerator or without meaning and without repetition, therefore total permutations are possible, that is, the permutation of the 5-letter word swing, taken 3 at a time is equal to 5 factorial divided by the factorial of 5 minus 3. Since 5 minus 3 is 2, we can cancel out 2. So, only the numerator is left, which is 5 times 4 times 3 equals 60. Another solution of the same problem. How many 3-letter words with or without meaning can be formed out of the letters of the word swing when repetition of letters is not allowed? Solution: this problem can be also done by applying the multiplication rule. Since 3 letters are to be formed and repetition is not allowed, We have first letter equals 5 choices. Second letter equals 4 choices. Third letter equals 3 choices. Getting the product of 5 times 4 times 3 is 60, the number of 3-letter words formed from the word swing if repetition is not allowed. Another problem about permutation. How many 3-letter words with or without meaning can be formed out of the letters of the word smoke when repetition of words is allowed? Solution: the number of objects, in this case, is 5, as the word smoke has 5 letters and 3-letter words are to be formed. Thus, the permutation of the word smoke taken 3 letters at a time when repetition is allowed is 5 cubed, which is equal to 125. By multiplication rule, we get, first letter equals 5 choices, second letter equals 5 choices, third letter equals 5 choices, the choices remains 5 since repetition is allowed to happen. So, 5 times 5 times 5 is 5 cubed is 125. There is 5 cubed since simply add exponents when you multiply powers of the same bases. 5 is understood to have a power of 1. If there are n items to be arranged, and only r items are taken at a time and no item is repeated, the number of permutation is computed by using formula. The permutation p of n items taken r at a time is equal to the factorial of n divided by the factorial of n minus r. Another example, a zip code contains 5 digits. How many different zip codes can be made with the digits 0 to 9 if no digit is used more than once and the first digit is not 0? Solution: use this reasoning. For the first position, there are 9 possible choices, since 0 is not allowed. After the first number is chosen, there are 9 possible choices for the second number, since 0 is now allowed. Then, there are 8 possible choices for the third number, 7 possible choices for the fourth number and 6 possible choices for the fifth number. That is, 9 times 9 times 8 times 7 times 6 is equal to 27,216. Using the permutation formula, we have an exclusion FO0. So we get 9 times the permutation of 9 numbers taken 4 at a time, that is 9 factorial divided by 9 minus 4, then, we have 9 factorial over 9 minus 4 is 9 factorial divided by 5 factorial. Since the denominator is 5 factorial, then we can cancel 5 factorial. This gives us 9 times 9 times 8 times 7 times 6 is 27,216. Combination refers to the number of ways a set of items or objects can be arranged. However, the order is not considered. Likewise, the number of combination for a set of n items taken at a time is always 1 because the order is not given importance. If n items are arranged r at a time and order is not considered, the formula is given below. The combination C of n object taken r at a time is equal to n factorial over the factorial of n minus r times r factorial, where n is the total number of objects. R is the number of objects selected or taken at a time. Let us have another problem. In a lottery, each ticket has a 5-digit number using the number 0 to 9 on it. A. You win if your ticket has the digits in any order. What are your chances of winning? B. You will win only if your ticket has the digits in the required order. What are your chances of winning? Solution: there are 10 digits to be taken 5 at a time. Now, solving for the first problem, we get the idea that the order of the numbers does not matter in the problem. Hence, the permutation formula shall be used in this problem. That is, the number of permutation p of 10 numbers taken 5 at a time is equal to 10 factorial divided by the factorial of 10 minus 5 equals 10 times 9 times 8 times 7 times 6 times 5 factorial divided by 5 factorial. Cancelling 5 factorial in both the numerator and denominator, we have the product of 10 times 9 times 8 times 7 times 6 equals 30,240. Therefore, the chances of winning is 1 out of 30,240. For the second problem, combination is applicable since order matters. Hence, the number of combination C of 10 numbers taken 5 at a time is equal to 10 factorial divided by the factorial of 10 minus 5 times 5 factorial. Then we have 10 times 9 times 8 times 7 times 6 divided by 5 factorial is equal to 252. Therefore, the chance of winning is 1 out of 252. Difference between permutation and combination. The major difference between permutation and combination are given below. Permutation: selection of the objects, where the order of selection matters. Arrangement of objects taken out of n objects. That is, the permutation p of n objects taken r at a time is equal to n factorial divided by n minus r factorial. Combination: selection of the objects, in which the order of selection does not matter. Selection of r objects taken out of n objects irrespective of the object arrangement. That is, the combination C of n objects taken r at a time is equal to n factorial divided by r factorial times n minus r factorial. Thank you for watching. Please share this to the learners.